Yeah, then let me directly start with my talk on the progress made in MultiCycle. And this is, in this case today, dealing mainly with the composite waste that we have treated in that project and the recovery of automotive relevant materials. Let me start with a very quick overview, just as an example to show you where we can expect, for instance, fiber reinforced materials, composites in automotive applications. And there are many pictures like that in the internet. I just took out one which is, let's say, citable. So this is one from 2013 from Friedrich and Al-Mahid. And they just mention here, and probably you can see it here, that many different companies, OEMs like BMW, Porsche, Audi, Nissan, and who else is here, Daimler, they are all using composites. And if they are a bit more precise here, you all see that they have glass fiber, polyamide, glass fiber PP in their glass fiber PA66 in comparison to PA6 here. Again, PA66 with glass fibers. In these structures, which is a bit missing in this picture, is that, of course, also carbon fiber materials are out there at the moment. For us here, it is very important to see that it is a kind of evolving material if we consider that as an in-feed for recycling. So what we get back for recycling, when we consider end-of-life vehicles, we of course need to know what has been put into such a vehicle 10 or 20 years ago. And therefore, in the end-of-life materials, we just see that material starting up. However, each of these materials that we see here is, of course, not only present or is not built directly at the OEMs. It is built somewhere in other companies like Tofaş, for example. And these people or these companies also have probably some residual waste. So it is not only that we have composites in post-consumer waste, we also have it in post-industrial waste. When we consider this material to be recycled, then let me start on the left-hand side. The current situation is more or less, we don't really have a good idea. And that means we do incineration here. And at least we can recover some CO2 and energy. But there's not only CO2, but there's also NOx's, and there's some other emissions which we all don't like. The other idea is, of course, chemical recycling. Here we have more or less two ideas. The one is depolymerization, which may be useful for polyamides, or we have a kind of pyrolysis, thermolysis, which is a feedstock recycling. Both have in common that in the end, if you go back to polymers, you have to start from feedstock or from monomers. You go very, very far back in the value chain to get something which can then be recomposed to polymers. In contrast to that, we have material recycling. And here we have the classical mechanical ones. We all know where you take the in-feed, you have a shredder, you have some cleaning ideas, mainly mechanically, some washing, some sifting, metal recovery, whatever. And in the end, there's something which is rather purified polymer and which is then re-extruded, melt filtered, and so on. This works quite fine, but not really well for fiber reinforced material with glass fiber contents up to 50%. Another idea could be the solvent-based technology, which I will present here today. Both have in common that they keep all the time at the polymer level. So there is no degradation down to monomers. And this is important since we, of course, want to have an economic and an ecological sound processing. Economic, and ecologically sound is a bit critical for chemical recycling, since all the energy which has been put in polyamide and polypropylene earlier is destroyed in this step here. And it means after all the long way back to the monomers, we have to reinvent or reapply the same amount of energy to come back to the polymers. So this is something where we have just theoretically very high CO2 emission or CO2 footprint in our backpacks. The same is true, that's not only ecologically, but also economically a bit critical. With material recycling, we keep that energy on the one hand, and we also have the idea or the request that the material quality that comes out in the end is good enough to go back into the cycle. And this is sometimes critical with respect to mechanical recycling. Here, fibers in there are critical. If you have to shred it down to very small pieces, you not only have glass fibers in there, you also will see some metals in the melts. So it is critical here. What we aim to have is a solvent-based recycled material, which is still a polymer, but which is that pure and that nice that you really like to have it back in your value chain, that you really like to have that as a feedstock for your automotive products later on. Very shortly, the solvent-based recycling technology starts with the waste, uses a solvent, and this dissolves the polymer on a polymeric level. So it is not degrading, it is still a polymer. Then you can start to purify the dissolved polymer from all the non-dissolved material, which might be dirt, metals, screws, whatever might be in there, sand from any, let's say, storage as a waste stream, and even some volatiles and, let's say, legacy additives might be here, get out by this one. If we keep on that track here, we see then a purified liquid, which is containing the polymer. After drying, meaning reconditioning the solvent, we get a recovered polymer, which is in the final drying stage, regranulated in an extruder. What here is named as a residue is, with respect to fiber reinforced materials, not a residue by itself, it is the fibers. And the fiber fraction is, of course, or may, of course, be useful for another second application. And this is also what we have investigated here. Very shortly, just to explain, this is a very general concept, and it's applicable to all thermoplastics. So when we talk about waste here, we only consider, let's say, at least 60% of the waste stream to be one of the target polymers that we have. The solvents that we're using are solvent specific, and they're safe, and it allows us to separate impurities and contaminants, and in the end it is a very pure one. It's free of foreign polymers, free of impurities and harmful substances, and quality-wise it is competitive with virgin. I was asked to talk about the progress made in the MultiCycle project, and that also means that I have to define what was the starting point in 2018. And honestly, we do that solvent-based recycling since 1997, 96. That's when we started in the labs. However, at that point, we had a solvent-based purification or dissolution established for multiple different waste streams and polymers in our labs. And we had a small technical scale line, which was used for all these trials. Here you can see pictures of that. You see people are doing manual manipulations. Of course, there are pumps from one reactor to the other one, but it's not at all automized, and it's not really connected. And the whole area here is is in more or less one ARTEX zone, so it's nothing which is in that scale directly scalable to industrial or commercial scale. However, we had at that time a successful upscaled into an industrial scale plant in Indonesia for pure polyolefins, only for multi-layer films, and they were then recovered from landfills in that area. For all other activities, including PO recovery from, let's say, European multi-layer films, we had no demonstrated plant available. And if you see here the capacity that we can run with that plant, it is, for an industrial scale, ridiculous. And that makes it very, very critical to get samples for demonstration scale. And that means we had no technical scale production of multiple polymers from multi-layer packs and not at all for fiber reinforced materials. Then, in the very beginning of our project, we were supplied by the project partners with different fiber reinforced materials from the automotive sector. You see here the polyamide 6 with glass fibers, polyamide 6,6 with glass fibers, PP with glass fibers, but also a bit later on then a PA11 with carbon fibers. And we got a bit more complex waste streams throughout the project. Here something, it is a complete part made of different materials. You can see the mouse here. This is made of PA6, but different parts, one containing glass fibers, others containing carbon fibers. Same is true for this one, which is really a post-consumer material recovered from the company GBP in Spain, with the aim to enrich polyamide with carbon fibers in there. Yeah. Also, in the very beginning, we started with some lab trials, and here, this is just to show you how that looks like. Well, so in the end, we dissolve it and we get back the recovered polymer, and here you see some melt flow strands that were produced. They don't look too nice in the very beginning. Here you see the recovered glass fibers in that, carbon fibers in that case from such a material. And we do some mass balancing here and see, okay, if we don't really wash that once or twice, the carbon or the PP yield is well below what we like to have with more than 60%. Okay, the objectives of what we're doing in MultiCycle is not to keep at the lab scale level and to improve things in there. We wanted to see how to engineer and to build a pilot plant as a versatile demonstration capacity for both automotive and packaging. We wanted to operate that new built plant at scale, making use of feedstock which have never been or which are not suitable for mechanical recycling. And in the end, we of course were asked to provide sufficient material as granules suitable to build automotive demonstrator parts with recycled content. This will be part of the next talk. So what we were asked for is here engineering skills. Please build a new plant. Then once that's built, we need operators who can do that at scale. And finally, these are not necessarily polymer experts here. They were asked to produce quality skills, to have the quality skills to see that the products which come out are really good enough in terms of competitiveness to virgin polyamide or polypropylene. Let's come to what was then further defined. What is the characteristics of our pilot plant? Of course, it was the scope to prove technical and economical feasibility. It should be versatile, different waste streams, polymers, including the use of different solvents. Since, of course, we have different polymers, we need different solvents. That's easy in lab, but not easy in that scale. The capacity is far below economic scales. So we consider an economic scale in the range of 5,000 tons a year or higher. And of course, such a small scale pilot does not contain all features of a commercial scale plant. So one of that is, for example, the cleaning devices are not fully optimized, since they had to provide a compromise for fiber reinforced plastics, glass fibers, carbon fibers on the one hand, and residues from multi-layer packaging end of life. Here we have residual foodstuffs and whatever in there, which is a bit a different cleaning task. And of course, not fully automated, and we had still some minor manual operations, but very, very minor. It was, in the end, to be honest here, very challenging for planning, construction, and finally also in operation. However, in the end, we managed to produce to provide an upscale pilot plant at TL7 with a nominal capacity which looks rather low, but if you see how large the plant is, it is probably just to demonstrate that each of these containers that we were using here is just a bit smaller than in industrial commercial scale, but all the rest, all the surrounding supply, whatever, needs to be more or less in the same scale as we need for commercial one. We have a hall here with 800 square meters, 7 meters height, a plant floor space of 350 square meters, 820 single components, and more than 1 kilometer of piping. And we also had to fulfill the ATEX directives. It is really huge work. It's we cannot really show that in all pictures. It is just congratulations to our partner Lömi, who fulfilled that in the end, gratefully. Let's go back to the fiber reinforced materials we got from the consortium, and here you see that we finally focused on the PA6, PA66 glass fiber material, and the PP glass fiber material. Why? The PA11 carbon fiber was not supplied in sufficient amount. Sorry. The PA66 carbon fiber glass fiber is not much more challenged than this one here. However, in our filters, we cannot distinguish between carbon fibers and glass fibers. So whatever we do here, it doesn't bring any added value. So we decided not to use that one as an in-feed for the large scale demonstration finally. And which was one of our most wanted materials, the polyamide with carbon fibers from post-consumer, was supplied. It was of course, well characterized up front, and we unfortunately saw that neither the polyamide content was good enough, and also the carbon fiber content, not only carbon fiber, but also glass fibers. And what was much more critical, there were so many other different polymers and metals in that our plant was not prepared for that. So it's not a general no for CreaSolv, but for the installation that we have built up and upscaled, it was not suitable. Yeah, let's go now step by step into the recovered materials. Let's start with the glass fibers. So the separation of the glass fibers from PA6, PA66, and PP works quite well in pilot plant. The recycled polymers does not contain any fibers anymore. And yeah, for the glass fibers, here you see how they look in such a process. They are unfortunately too short for fiber reinforced applications so far. So this is why we had no chance to bring it back into glass fiber reinforced materials in this project. However, what we tried to do successfully was to mill that down to have a glass fiber filler material, and this could of course be used as an additive in filled glass fiber filled materials. Polymer wise, here just examples. The in-feed material for polypropylene. You see here the recovered one, really free of any glass fibers, and here you see the resulting DSC spectra here, curves, and a very, very clean one. You do not see any other polymer in here. So it's a very, very good result for us. Same is true for the polyamide 6, very pure one, only PA6 in here in the DSC. Also very shiny surface material, looks quite well. And the same is in the end true for the polyamide 6.6. Sorry for not providing here any mechanical data. This is more or less what is then part of the next talk. Finally, we were then asked to also provide, of course, carbon fibers, since carbon fiber, running carbon fibers in a circular economy would be a great benefit for all of us. We had to go back in the small technical scale plant here in this case, only because of having the capacities. And let's say we decided very lately in the project to do so. However, here you see, on the one hand, we get back with a rather pure recycled PA11. It works as the other polyamide, so there's not much of a difference for us. The recovered carbon fibers, here you see some pictures. They also look very, very nice in terms of diameters and lengths. They are fine. The length of the carbon fibers are, of course, not endless, since the materials were chopped before we could bring them into the dissolution containers in our plant. So therefore, they are not as long as probably all of us wanted to have them, but in the end, good enough to get some checks. Let me summarize at that point. The CreaSolv pilot plant at demonstration scale was functional, robust, versatile, and for us, it was really the industrial proof of the concept. We had many, many different feedstocks of the fiber reinforced PP, PA, post-consumer materials mostly. And for the post-industrial, we have seen that this would require either another pre-treatment to get out of some of the other polymers and some of the metals, or to have an other cleaning or purification concept in that plant. Also doable, no rocket science, but not doable in the middle of the project when all the engineering was done. And this goes back to, let's say, the engineering skills that I mentioned in the beginning. Now we come to the operator challenge. Yes, it was possible with people who have never done that before to run such a plant with even multiple polymers, multiple waste streams from automotive and packaging. And it was really, really hard work in the beginning. We had long learning curves also in the beginning, but finally we were really able to provide materials in sufficient volumes for the demonstrators later on. And finally, let me come to that point. The plant is still existing and it is not planned to destroy it after the project. So it will still be available for further trials to prepare for commercial scale plants, to train operators, or to produce just some samples for any of interested third-party companies here who may say, okay, let's try if this process works also with my post-industrial or with this specific post-consumer waste stream. So you're really all invited to get in contact to us if you want to do such trials, if you want to scale up such a process with us. Thank you very much.